Well, thank you very much for the introduction, Nathan, and welcome to everybody. Glad to be able to do this. It's if there's one benefit to COVID, and hopefully there is one benefit, it's that we're growing closer as a global community through the wonders of the internet. So it's really quite amazing to be able to sit here in Reno and talk to people across the globe. If there's anyone here from Europe or Africa, I hope you're enjoying the middle of the night. To everyone else, good morning or good evening. So without any further ado, let me move into just an outline of what I'll talk about. I'll just quickly talk about instrumentation and how we capture data. HSI refers to hyperspectral imaging. A little bit about the importance of an additional wavelength range that we use called the long wave infrared or thermal infrared. A little bit about data processing and information extraction, just because that goes to how we use this information for geometallurgy. Then I'll show you two types of applications. One where we use direct mineralogy, so we identify a mineral species that we're interested in, or where we take the information and in toto and use that to build predictive correlations that we can then apply to mining or exploration feasibility sites. So hyperspectral instrumentation, the granddaddy of it all was the old PIMA, which came out of the CSIRO's initiatives in the late 80s. It got commercialized in the early 90s. And I joined Anglo American and De Beers in 93 and was given this little white box and told to figure out how the hell it worked. So that was my introduction to spectral geology, and it was an interesting one, I must say. The PIMA was kind of the first time. Spectral geology has been around since the 70s. Seminal papers by Hunt in 1970 and 73. But this was the first time it kind of was brought to the masses, so to speak. So we had a really practical instrument people could use. That's then morphed through into today's technology, which is the TerraSpec. I would guess would be the industry standard for the point measurement systems, with a couple of challenges to that thrown. And then we've also got automated point measurement, the high loggers, which are dotted all around Australia in the various geological surveys. It's just a way of collecting the same kind of point measurement information, but in an automated, much easier fashion. And then that led into the development of the hyperspectral core images. We use pretty much the same cameras that airborne people use to map the Earth hyperspectrally, but obviously in a slightly modified fashion. So what we really do for this technology is we irradiate a surface with either heat or with light. The heat in the thermal or long wave infrared, and light in the visible near infrared and shortwave infrared. And the interaction between that incident energy and the target results in scattering, basically, of that incident light. And we measure that reflected scattered light, and that reflected scattered light gets absorbed or scattered preferentially in the long wave infrared at certain wavelengths. And the combinations of where it gets absorbed in the short wave or reflected in the long wave is characteristic of the mineral species that we're looking at. So on the bottom right are just a few different mineral types. And after a while, you get quite proficient in looking at a squiggle and figuring out what the mineral is that you're dealing with. So this would be in the hyperspectral imaging sense. We run a camera over a box of core. We have pixels of information that we collect, anywhere from 0.3, 0.4 millimeter square pixels all the way up to maybe 1.5 millimeter square, depending on the application and the technology. And with that, we have the ability to see what minerals are present in each pixel. So there's two pixel spectra, one of illite and one of calcite, from close together on this particular box of core. So this just shows you how the method works. What we're able to do with it then, obviously, is to identify and map various mineral species. We can do a little bit more, and I'll get to that in a second, but this is for many people, the most important part of it is the ability to identify minerals. And The addition of the long wave infrared, which is the column on the far right, brings in a lot of minerals that are just simply not detectable in other wavelength ranges, and that for the simple reason that in the long wave infrared, we measure a bunch of fundamental bonds between elements, including silicon and oxygen, aluminium and oxygen, magnesium and oxygen, etc., etc. So we can measure those fundamental bonds, whereas in the shortwave infrared, we're measuring bonds that are related to water or the hydroxyl or to CO2 bonds actually. So that means we are restricted to minerals that have either CO2 carbonates or contain water, which would be the phyllosilicates and the hydrous sulfates, etc. So the long wave infrared brings a wider range of minerals to bear. The one thing I would point out at the bottom is sulfides are non-diagnostic across all wavelength ranges. We can see their presence, but we just generally can't tell you what sulfide is. And the next slide is an example of that. So this is a box of core from a project in Peru. On the left is a false color composite image built from the long wave infrared, and all of those little white bits on that image are sulfides. Being specular reflectors, they're uniformly bright, so they appear as bright white spots no matter which band you're looking at. And on the right, you can see the sulfides that are related to those little white blebs. Now, in this case, the sulfides are chalcopyrite, bornite, and pyrite. But unfortunately, we can't tell you which sulfide you're looking at. However, just the information that you're able to extract in terms of mapping where they occur allows you to go back and be a bit more rigorous in the logging of the core to get better information about the abundance of the different sulfide species. Right, so in terms of the long wave, I've already mentioned, we add a little bit in terms of the minerals. So this is a scan system. And what you can see on the left is the short wave, the middle image, I should say. On the left is the color image of the core. In the middle is the mineral map constructed from the shortwave infrared, and you can see there's a lot of blue, which in this particular case is saponite, which is the magnesium smectite. It's present in very small amounts as a retrograde or weathering product of skarn minerals, calc-silicates, etc. It's present in very small amounts, but because we can't see the underlying mineral that it's forming on, we estimate that there's a heck of a lot of it, when there might not actually be that. It might not be 100%, obviously, of the core is saponite. It might only be a few percent, but it's all that we measure, so it looks like it's 100%. Whereas when we add in the long wave on the right, you can start to see the variations from biopside to the various garnets, etc., etc. So adding the long wave brings in that extra layer of mineralogy that can be critical in defining an ore system. And then the other thing that the long wave infrared brings is it gives us the ability to see variations in grain size and in mineral texture that we simply can't see anywhere else. So this is an example for quartz. It works pretty well as well for carbonates, and we're able to map grain size of quartz based on the spectral signature. It has applications in the mining world, but the oil and gas guys are probably the biggest beneficiaries, because this is a way of separating sedimentary orthogenic quartz from quartz cement. Right, so in terms of what we do, we take our instrument to a site, we run lots of core through it, and then we've got to make sense of what we've got. And we do generate very, very big volumes of core. Sort of a rule of thumb is when we've got a full system with 3 hyperspectral cameras and the RGB color imager, we generate about 1 terabyte of raw data per 10 kilometers of core that's imaged. That obviously then doubles when we do a reflectance correction, and we've then got to process all of that. So we've got a terabyte or more of data at a time. So we need pretty robust software. We need to be able to do this quickly, but we also need to maintain a good degree of accuracy with the work. So we've got 2 main algorithm types that we can apply. One is a supervised, where we would match to a library. We put in a library of spectrum. We say, right, which library spectrum does each pixel match closest to? And we build a map on that basis. Or we can use an unsupervised, which is a slightly more objective approach, where we mine the data and we ask it what's in there. via, in our case, we use a combination of M-member selection, unmixing, and then a classification, a neural network classification. So we as a company employ both of these approaches on all projects because they do complement each other quite nicely, and are fit for slightly different purposes. And then very importantly for geometallurgy, we do a numerical data extraction. So talk to you about that. We do the mineralogy, as I said, via an interpretation, but it's very 1D in that we're making a decision about a pixel, and that's our final decision. And what we're doing is we're removing some of the information content. There might be something in there that's related to its brightness or its shape that I, as a spectral geologist, simply can't distinguish adequately. So I would call different things muscovites, even though they might be slightly different. So there's a strong influence by the geologist. And to be fair, if we take this mapping into geometallurgy, it's generally not the optimal product to be using. It's a bit of a disaster. We then do also extract numerical data. So this is unbiased. You could call it almost like a spectral assay, because all we are measuring is the absolute raw response of each pixel. And we're looking at the depths and wavelength positions of absorption features, or the peak heights and the wavelength positions of Rastrallan peaks, they're called in the long wave infrared. And those give us a proxy for abundance, and they give us some information about composition. We can also extract various ratios of these. We can extract slopes of inter-absorption stretches on the spectral signature. And then what we can use these for is we can apply Boolean mineral indices, a decision tree, basically. And that allows us to then build a more accurate mineral map than we're able to do using either of the matching or the classification approaches. I would point out, though, that with the Boolean approach, the cutoffs that we apply, because at some point we've got to make a yes-no decision, those are absolutely critical, and they can influence things a little bit. So as we go through, I'll explain to you how these different data types get used for the different geometallurgical applications. These are obviously all expressed as images, so as we can look at the textural relationships between minerals, but we're also able to extract downhole composites for modeling or correlation. And you can do that at basically any spacing you like, from one image line through to whatever width you would prefer. In general, what we try to do is match to the assay spacing of a project, because from a geometallurgical perspective, everything then is at a common spacing, and we can use that to build models. Okay, so switching very slightly now to where we fit within geometallurgy. This is a pyramid that was put together at JK-MRC many years ago for the P843 project, and remains absolutely valid. And within that, we've got various types of data that we're able to acquire. So we've got, you know, the normal metallurgical composite work that metallurgists go and collect to do their plant design. Unfortunately, that's not necessarily representative of the ore body and how it's going to perform when you start mining it. The industry has been, I guess, guilty over many, many years of assuming that to be the case. And there've been many failures of projects because of the fact that you're not mining 100 million tons of ore in one go. You're mining it in small chunks, and each of those chunks is not the same as another chunk. So geometallurgy was designed to try and bring that spatial variability of ore performance into the equation. So for that, what we do is we've got what we call reference or truth data, and those will be a lot of different types of tests, bench tests that have been developed specifically for geometallurgy. And in fact, most of those developed in 843 were developed at the JK-MRC, things like the rotary breakage tester, the modified bond index, modified or small scale flotation tests, batch flotation, as well as small scale leaching using things like the Lithological tablet. So we can use those data to build a reference of performance, but that's going to be done on a fairly small volume of samples, simply because we can't afford to do it on every single piece of core that we drill. just becomes prohibitively expensive. So the idea then is, can we link that in some way to cheaper data? And we've got two levels. The most important really is the level one, what we call the proxy data. It's because there's information in there that's related to ore performance, but it's not directly related to ore performance. So we can't say, I've seen X, and that means Y is going to happen. It's a little more difficult to get to that kind of value judgment. But what we tend to do is collect those for every single sample of core that we drill. And in those proxy data types, the main ones that people would use would be geochemistry, ICP, or XRF geochemistry, little hardness testers, the Equitip or Schmidt hammers, geophysical tools, magnetic susceptibility, sonic loggers, etc. Density could be added to that. A lot of people collect density at that very fine scale. And then what we do is part of that hyperspectral mineralogy, because when we image the core, we image every single piece of the core continuously without missing anything. So we've got a complete record of the core in a hyperspectral sense. So that's where we fit in. So the idea is, can we take our hyperspectral data and relate it in some way to the ore performance data? And I've got two case studies later to show how we do that. But first, I'll just show you, well, jumping a little bit ahead here, I will show you how we can use mineralogy on its own in certain instances. So points to consider, we've used this technology now on multiple commodities. We've done geomet projects on copper, on gold, precious metals, zinc, PGEs, diamonds, phosphates, believe it or not, an apatite mine. Our data are not necessarily, the mineralogy, extractive mineralogy is not quantified. And there's a bunch of reasons for that that would require a really in-depth discussion that we don't have time for. But to get to quantifiable mineralogy, we can calibrate to XRD or to AutoSAM. And there's quite a lot of literature now within the journal body that discusses exactly that kind of work that can be done. And for the oil and gas guys, we do routinely an XRD calibration of the hyperspectral data, because what it does is generate basically proxy XRD data in between sample points. So it gives a continuous mineralogical or calibrated mineralogical plot for a borehole using XRD as the calibration. Also make the point that although we do collect fantastic and wonderful data, it's not everything. And while we have used it as a standalone, we've always found that integration with other data sets is better. So where you've got things like geochemistry and an Equitip, etc., it's good to be able to pull all of that together in a multivariate sense. And then horses for courses. We don't capture sulfides or metals. So for example, precious metal leaching is a very difficult thing to do using hyperspectral data, unless there is a relationship between the gang mineralogy and leach performance. And I will show you one example where we believe that to be the case. And we can use this to, as I said, for the numerical data that we can correlate, or we can directly map problem minerals. And I've got a couple of examples that I'll show you where we've done this. The first one being mapping of clays, and in this particular instance, smectite clay in particular can be an issue in the crushing circuit because it can end up coating things and it really can reduce crushing performance. So we've had a lot of requests from people to please just map the clays, but not all of the smectite clays are equally guilty. Montmorillonite is by far the most destructive of them, and saponite would be less destructive, although in some kimberlites, saponite is a big problem. So we're able to, using this Boolean approach, we can develop a smectite index. In this case, it doesn't matter what the smectite is. We've just said, let's find the smectite. And then we can extract that. You can see the textual relationships on the image. And then the downhole plot is on the right, just of Montmorillonite in that case, where you can see how Montmorillonite is distributed down that same hole. So clays are fairly straightforward. And in fact, Clay speciation is incredibly easy using spectral technology. It doesn't require multiple analyses like you might have to do with XRD. It's a once-off and very quick. So, you know, speciating between kaolinite, smectite, illite, and the other clays, and then within the smectite, speciating those smectites, very easy to do. An example where this is a phosphate mine, and they find that where they get excessive dolomite, the magnesium in the dolomite for some reason inhibits the flotation of apatite. And what they were interested in being able to do is to map out where they've got dolomite and where they've got calcite. So the image on the bottom right shows where there's dolomite in blue and calcite in green. So you can see a fair amount of dolomite shot through, and we can extract this obviously in a downhole sense, build a model, and then build some kind of a predictive recovery index based on that. And then everyone's favorite, if you're a metallurgist, is talc, because it's just an absolute nightmare. And talc, in this particular case, this is a mine in Nevada, causes overfrothing of the flotation circuit. And when that happens, they have to shut down, clean up, and then restart. So they're losing froth onto the floor, which is basically being swept away. And at the same time, they're losing productivity. So in an average year, they might have 7 or 8 shutdowns, and each of those can cost them, you know, anywhere up to $100,000. So they prefer not to shut down at all. So they need a talc prediction, and it's very easy to do. What we've done is taken blast holes, imaged those. You can see on the left is a talc heat map where we've got red, that's pure talc, and where we've got those dark areas, there's actually sample, but there's just no talc present. So what we can do then is agglomerate all of that information from that image, give it a number, give it a talc score, and then we can plot that back into the pit. So on the right is blast holes scored by their talc number, going from a lot of talc at 0.1 all the way down to 0 talc at 0. And you can see the talc is along the edges of the pit, which is to be expected. It's on the contact, it's a skarn. So it's on the contact of the intrusive and the skarned sediments. And the little green polygons are where they encountered overfrothing issues from the bench above. So there are 3 overfroths from the bench above, which are the green polygons, and 4 overfroths. And what's interesting is you can see that in some cases the talc persists down onto the next bench, which is where we've measured it, but in other cases it doesn't. And we've got new talc appearing that wasn't present on the bench above, either because this lower bench is cut into maybe into some newer rock, or because the talc itself, besides having some kind of a vertical distribution, in other places has a horizontal distribution. So this is really useful information, and then using this, they can decide on whether they're going to de-slime those particular areas, or as they are choosing to do, blend this material in at a very low rate with run-of-mine feed, and that way keep their talc threshold below overfroth levels and be able to process it. They can't throw the talc away, unfortunately, because it carries good grades. A nice example, this from Mexico, where we had a project with zinc recoveries that suddenly fell off a cliff in feasibility, and they couldn't understand that because they couldn't see any evidence for why it might be the case. They suspected maybe it was clays causing it, but it turned out actually to be zinc substituting into siderite. So this is proto-oxidation of the ore. So we've got sphalerite, which is altering to a zinc-rich siderite in the red, and then we've just got good old siderite as an alteration product in the blues and purples. So we can now start to see and quantify the amount of zinc-rich siderite within a sample, which then obviously helps. Iron ore, this is a magnetite mine, and they need to be able to map hematite, because hematite, being non-magnetic, doesn't go through the magnetic separator, and hematite is spectrally responsive, magnetite is not. So this was quite an easy and interesting scenario to work in. Again, just quantifying the amount of the mineral present. And then it's not to say that minerals are always bad. As Nathan will know through work that Anita's done over the years, we've got a lot of mine projects around the world where we just simply don't have enough neutralizing capacity, and we've got an acid generating waste. So this is an example where we were tasked with finding carbonate, please, and mapping it out, because that's really important. Wherever they can find carbonate, it's worth their while to actually mine it and add it to the waste rock dump so as they can mitigate a very, very pyritic ore from creating acid. And then a last example, which is quite a nice one. This is a gangue mineral proxy. This is from the Bushveld complex in South Africa, where contrary to popular opinion, there's a heck of a lot of alteration. And what the alteration does is, in some cases, it brings in specifically deleterious minerals like talc. But in other cases, just the incipient alteration and the development of minor phyllosilicate is an indication that we've hit a zone where there's been significant post-mineral fluid flow, and that the ore mineralogy itself may have altered. So the Bushveld, typically what they like to mine is PGEs associated with coarse pentlandite and chalcopyrite. That's easy to recover by flotation. But when they hit these altered zones, they find that a lot of the PGEs start to move into arsenides, tellurides, become native metals, etc. And those don't recover necessarily quite as well through the flotation circuit. But knowledge of that means that they can switch reagents to try and capture these a little bit better. So this is an instance where you can get some feel for leach performance just based, for recovery performance based on the gangue of the ore and not on the ore mineralogy itself. Okay, so now I'm going to take you through two case studies, and I'll try and get through them relatively quickly so that we've got time for questions. Both of these are not brand new. Unfortunately, a lot of the work we do is, unfortunately subject to confidentiality, but these are two that we can show, and this is one that we started working on. In fact, it was our case study that kind of got the whole core imaging thing going in Anglo Gold. It's a project in Colombia called Colossa, which is now sadly on the back burner for a bunch of reasons that are non-geological. It's a very, very big porphyry project, 32 million ounces of gold at about 0.8 grams per ton, billion tons of ore there or thereabouts. No copper, for whatever reason, absolutely no copper. It's one of the world's very few gold-only porphyries. One of the things about it, though, is, and this was quite early on, the metallurgical test work showed that the ore is extremely hard. So the AB breakage number is around about 30, which is very low, and a bondwork index of around about 16.5. These were on the original composites that were collected. Is really hard. You know, most porphyries are probably running in the 10 to 12 bond range. So this is significantly harder, and they're probably running around about 50 AB. So immediately there was always some feeling that this was going to be a tricky project just from the point of view of comminution. They brought in a Chilean, a group of Chileans with experience in mega projects to work for Anglo Gold on this specific project, and these guys ran the numbers and figured out that with the grade and the fact that this had to be an open cut, it needed to be mined at a heck of a rate. And to do that, 65 million tons a year, which is about 6,200 tons per hour, which is in the Escondida, Chuquicamata type range of operations. So this would be one of the biggest mining operations on the planet. And that required a PFS capex of about 6 billion. Now at that point, we'd just gone through the global financial crisis, and Anglo Gold's entire market cap was 4 billion. So being able to raise 6 billion for a fairly risky project was just a step too far for the board and the executive committee to accept. So part of what needed to be done was to do a proper geometallurgical study. And what we had to use, this was the first time we really systematically imaged a project. So we captured 150,000 meters of shortwave data in 4 separate campaigns. They've got had a 2-meter assay sample spacing. So, and each one of those 2-meter sample assays had ICP analyses, 49 element with the 4 acid hydrogens. So really high quality ICP, 75,000 out of those. Magnetic susceptibility and sonic logger were collected across the entire project. We had a poor girl who went mad. She did equitip at 2-centimeter spacing. So you can imagine for 150,000 meters of core, that took her almost 3 years. That's the only thing she did every day. It was just bounce and equitip off core. It was the most soul-destroying thing I've ever seen anyone subjected to. And then in addition to that, at JK, we did around about 280 A/B tests using the rotary breakage tester. We had 434 bond index, mostly modified bond index tests. And then we also did some sag power index through SGS, mostly on 2-meter samples, but up to 10-meter samples, some of them were. Because of the way the project had evolved, we couldn't really get back in and say, you know, we need to domain this using all of this data, because a lot of this data arrived once things had already started to happen. So we weren't in a position to say, well, let's take all of our data and domain it and then select our samples appropriately. So the samples were kind of selected more on a lithological basis rather than on a data basis. But nevertheless, I think as the results show, turned out to be quite fit for purpose. So what we did was we took all of the different data sets and we had a look at how those related to those bond index, SPI and AB tests. And what we found that a combination of hyperspectral and ICP geochemistry gave us the best data set to use to correlate against. So what we then did, we did a series of multilinear regressions. For this particular part of the project, there was no separation by lithology. We just simply treated the whole thing as one big entity. But we did do a little bit of domaining at a later stage, as I'll show you. And then one of the things we were a little concerned about was, well, how do we test this result? So we got a correlation, but is it overfitted? What does it mean? So what we did was we adopted almost a bootstrap approach. And we ran each of these correlations 100 times. And in each case, what we did was we kept back a random sample of 10% of the measured numbers, measured samples, as a test data set. And it always varied, it was randomized. And then what we could do is we could plot those up. So the plot at the bottom on the right shows 100 iterations of this. And what's interesting is 98 of them plot along that red line. So there are 98 sets of data in there. And then there are 2 that plot on that green line. So if we'd been unlucky enough to get one of those 2 green lines, we would have ended up with an overfitted model and bunkum for a result. So by doing this, what we did was we removed that overfitting risk, and we were able then to say, well, we've got 98 of these 100 runs basically correlate to 0.99999 to each other. So we can select any which one of those and use that for our modeling. So having then selected that model, we could apply it back into the 75,000 samples that we've got, the assay samples. And based on that, we could then plot up the results. So now we've got, instead of 280 ABs and 430 odd bonds, we've got 75,000 of each, albeit predicted with a slight error. And then we plotted those up. This is in Leapfrog, and we looked at the spatial patterns to see that they made sense. And what I'll just draw your attention to is a couple of weird and wonderful things. This hole over here, this stuff over here, which was a little wonky. You know, you're going from something that's low suddenly into something that's very high. And it turned out that these particular holes were drilled a long way away from where we had any kind of sample control. So they just kind of sat out on the edge of the data cloud. So all we did was remove those from any subsequent modeling. We just said we're going to ignore those holes because they're going to influence things. Having done this, the next step is to do what the resource people do and estimate between boreholes, so Craig between boreholes, and estimate bond, AB, and SAG power index into blocks. So we used the standard block model size, which was 15 by 15 by 5 meters, was sorry, 50 by 50 by 15 meters was the standard block model size for the resource. The smaller one was going to be for grade control should they got to mine. And then we were able to take that and Krigg it, just using ordinary Krigging. And what we found actually is that these rock properties tend to be a lot more predictable and continuous than grade, as an example. In fact, the resource guys quite like working with this because it was much easier. So we ended up now going through this process, produced a block model for each. And then based on that block model, we could transform those numbers into throughput. So what we could do is we could use the AB and convert that to a specific kilowatts per hour ton number for a particular block of ore. And then knowing what the equipment was, we'd be able to predict what the crush and early grind performance would be. Using the SAG power index, we could move a little bit further down the line and look at what would happen in the late stage SAG milling. And then using the bond index, we could look at what would happen in the bond index. So the original plant design called for 3 separate lines of crushers, primary, secondary, and tertiary crushers, followed by a giant SAG mill, followed by 2 ball mills. And then all of that going into a whole ore leach seemed to be the most effective way of recovering. So it was going to be an extremely big plant with difficulties because this is in the mountains and there's not a lot of real estate to put in a plant of that magnitude. But anyway, what came out of it was these numbers over here. And it was interesting to see that we had exactly 13% of the ore body that would meet or exceed the design criteria for the pre-feasibility. And there was a bit of argument from the metallurgists about the conversions that we used to get to the specific energies, and they were valid. So the models were rerun using their more optimistic numbers, and that increased it from 13 to 21%. So clearly, most of this was not going to crush or crush and grind at nearly the rate required to make money. So this was, I guess, along with a bunch of other things, the death knell for this particular feasibility plan, and it was all restarted with a completely different plan, the work for which was going on when I left AngloGold. So I'm not privy to where that ended up, but in any case, the project has now gone into market. What really the metallurgists like to see, though, is where these hard pieces of rock are. So being able to now show that spatial component of where you're going to be encountering the really bad stuff is quite a valuable way of communicating the nature of the problem. What we did notice when we had done the work, we had domained into 3 broad groups. There are 3 mineralized types. You've got oxides, intrusive rocks, and country rocks, the metamorphics that are variably mineralized. And we did notice that there seemed to be a bimodal distribution of throughput in the intrusives. And when we looked at it, it seemed that quite clearly that we could split that along lithology lines between the early and intermineral diorites. And what was interesting when we went and put the block model back together, this is throughput within the block model, and this is a section. What's interesting is you can see the early diorites are giving us fairly good throughputs, which then drops off as we move into the very little throughput. But the red over here is the early diorites, which are mantled by these intermineral diorites, and then they themselves are, intruded into the country rock. And what became clear was that the really hard material is related mostly to these intermineral diorites, which makes sense because they're albitic as opposed to potassium feldspar rich, and albite's harder. And we also found that the extremes of hard rock occur at an indurated and hornfels boundary between the interminerals and the country rock. So there's good geological explanation for what we're seeing. Okay, moving on to the second case study. This is an open cut and gold mine in Nevada. They've got multiple pits, and what they found was that on a day-to-day basis, things were just all over the map. Even though the ore geologists were telling them it was the same material, clearly the plant was telling them that it wasn't. It noted significant silicate entrainment with poor concentrate grades as a result, and their bottom line was being affected. So this is just some of the day-to-day type of variability that they were seeing. So you can see up to, over a 2-day period, a variability of up to 15 to 20% in throughput and 10% in recoveries. It's a very difficult thing for a plant manager to get his head around, and it does paint a very big target on his back, and people blame him always for that performance, even though he can't do much about it because he doesn't know what to do. And then this is some of the entrainment. This is XRF on the concentrate, and you can see quite significant calcium, aluminium, and magnesium entrainment in many of the cases. So the phyllosilicates are clearly floating. So what we did was initially, as a proof of concept, we had a little row of reverse circulation holes. These are 50 foot apart. Apologies, being in America, we're talking feet. 50 foot apart, and each hole was 100 feet deep. So we ran those through our system, and this was all given one ore type designation by the geologists in the pit because it's a fine-grained rock that nobody can really see too much in. But as you can see, it's mineralogically incredibly variable. So it's no wonder that plant performance was so all over the place. So we had some limited RC drilling, a lot of blast hole chips, no lab or bench tests. They didn't have money for those. So in the end, we had to send a guy into the plant with a shovel and collect samples twice a day from various places. So not exactly the most scientific sampling, but fit for purpose. And then it should be noted that, they're mining often from 2 different draw points, so in different pits. So we didn't have one single ore type that we could kind of hang against. We had variability of what was going through the plant. So this is now the mineralogy per day. On the top, the reason these are in here, the top one is for one ore type out of one pit, and you can see the amount of, this is out of the plant now, the mineralogy of the material entering the plant off the ROM, and you can see just how variable that is. And at the bottom is a blend from 2 different pits and 4 different draw points from within those pits. And what's interesting is I think that the amount of variability there is probably around about the same as you see in the single pit, single draw point. So clearly not an easy operation to work on. What we did was we collected all this data, and then we just had a look at daily throughput and daily recoveries. And what was interesting, don't worry too much about the details of these box and whiskers, but basically what they're showing is that for throughput, which is here, where we've got more mica, we get high throughput. Unfortunately, the bottom ones are showing that where we've got more mica, we get lower recoveries. So the Lord giveth and the Lord taketh away. So what we did then was we took all of that information and the spectral information and the plant information, and we built a deep belief network, because this is not something that you can restart each and every day as new data comes in. You want this thing to kind of learn as it goes, right? This is a true example of machine learning. You want the algorithm to learn and improve itself as new data gets added. And while these might not look like startlingly good R-squared values, when you consider the nature of the sampling and the fact that it's coming from so many different places, they're not bad, to be quite honest with you. And using that, what we could then do is we had also measured tons of blast hole chips, was we could take this back into the pit. So taking these predicted values back into the pit, matched exactly with their empirical knowledge. They knew that when they're in this fault zone, as an example, they get very high throughputs, and there's a simple reason for that, it's micro-rich. But they also knew that their gold recovery was disgusting, and there's a good reason for that, it's micro-rich. Copper recoveries were variable. Out to the west here, they've got a thermally altered granite where they know they get fantastically good copper recoveries, but they get very low throughputs. So everything matches very nicely to what they know about the operation. And then this can be used as using the blast hole information that they get, almost as a plant control, if you like, instead of a grade control, a plant control type of model. And what's interesting about this is the previous example was a feasibility study. This is an operational mine. So this is showing geometallurgy being used at two different stages, one in the resource definition and the second in the actual operation. So strategic versus tactical, if you like. Okay, so that's pretty much what I've got for you. I'll open up the questions. I can figure out how to do that in Zoom and answer whatever questions you guys might have.
Thanks very much, Paul. It was a really insightful talk and great to see your case studies as well. Paul, if you don't mind, just before we do go to questions, I just wanted to quickly pass over to Rick, and he just wanted to make a quick announcement to the people that are online, and then we can go back to the questions.
Thanks, Nathan. And can you hear me?
Yes.
Good. Yeah. So we probably should have done this at the start of the seminar, but time got away from us a little bit. I think that many of you online may know that Bill Whiten passed away on Monday. And so first of all, we'd really like to pass on our deepest condolences to Bill's wife, Agnes, sons, Paul and Joseph. And most of you will know, or many of you will know, that Bill Whiten's one of the founding fathers of the JKMRC. He'll be greatly missed. He would have really enjoyed this seminar. I've got no doubt about that. So Bill's journey into mineral processing, at least according to the legend, started one night in a computer lab when Albin Lynch, trying to solve a problem, ran into Bill, who was a young mathematician who didn't know anything about mineral processing at the time. And Albin Lynch recruited Bill in 1966, and the rest is history. He worked in mineral processing at the JKMRC until he retired, and despite his recent illness, he remained an active and positive student mentor virtually up to this year. And a lot of people who know him describe him as a mathematical genius. He's most famous for the Whiten ball mill perfect mixing model, but through his advice and mentorship, he influenced and shaped most of the mathematical models and simulators originating from the JKMRC over the past 50 years. He had a huge heart, and there are a lot of stories of him reaching out to students struggling with their studies, helping them work towards submission. And so we really want to pay tribute to his genius, acknowledge his contribution over the many decades to the JKMRC. And I just wanted to read a couple of the many comments that we've received so far from former students and colleagues. The first one, really sad news indeed. Bill was such a generous person. He was always able to provide advice, answer our questions during Friday seminars. He was really humble and kind with all the students. Bill Whiten has been an absolute giant in the world of mathematical modeling of comminution and mineral processing operations. Here's another one, and this was one that was repeated by a few people. I remember his office being piled high with papers with just a small space for his computer, but yet he always knew exactly where to find what he was looking for. And the final one I'll read, but there were many more. Mix genius with gentleman, and you get a bloke like Bill. So Bill's funeral will be held at 3 p.m. on Wednesday, 16th of September at Centenary Memorial Gardens in Wacol. And an email's gone around with contact details if you'd like to attend. We're trying to put a group together to go. And we're making plans at the JKMRC for further celebration of Bill's life and contribution, and we'll keep you updated on that. So we just wanted to pass that on, and thanks for your attention, and I'll pass back to Nathan and Paul now.
Thanks very much, Rick. Yeah, thank you. So yeah, on that note, anyway, we will get back to some questions here. Paul, thank you again for the presentation. I think it's been a really good insight. We have got a few questions coming in online, and you might be able to see those in the Q&A box. I'll probably go straight to the top one here from David Seaman, commenting on your great presentation. Could you describe some more about the correlation between Equitip and the hardness and competence testing? I suppose, given the intensity of the Equitip analysis, did it show meaningful results? And then there's another question here about the SPI prediction from spectral and ICP data. And can you give an indication of how many input variables were in the model, and what form of the spectral data was used in the regression?
Actually, excellent questions. So, yeah, and that's a very good set of questions. So, on the first side, first thing we did actually was to look at the relationship between the spectral data and the Equitip, and we found that the two correlated very, very strongly to each other. Interestingly, things fell off a little bit at the lower end of the Equitip, and that's probably because, Equitip actually works better when the ore's harder. You get a better result. So if somebody happened to hit a sulfide or a crack, you would get a dodgy number, and we could see if we eliminated sort of the bottom 5% of the Equitip values, we got an excellent correlation to the spectral data. What we also found, though, was adding the Equitip back into the full modeling exercise didn't actually add anything, because we could predict it reasonably well with the spectral data. So it didn't help us massively. Where it did help us, though, was on a slightly different line. We could use the Equitip with a simple blast model, which the guys actually, as part of the P843, favored, and the guys at CRC also favor, and the name of it escapes me at the moment, but it's a simpler blast model that doesn't require a whole lot of variables. The only one it requires in terms of rock parameters is UCS. And the Equitip actually correlates to UCS. There are a couple of papers about that. So we use the Equitip data as a blast predictor and not as a comminution predictor. Then on the second part of your question, which is the correlations, we ended up requiring, if memory serves, 6 spectral variables and 4 or 5 ICP elements. So the way we did it was we added them all, and we did a kind of a reductionist thing. So we just started taking them away and seeing if that made an effect on the correlation. And if it made an effect, we put that back in. And we just did that with every single one of the variables that we had, 49 elements, and I think 16 spectral variables that we included. And we ended up with that smaller number that we could use. And what was interesting was that the ones that were absolutely critical for prediction turned out to be interesting elements. One that was related, I think it was cesium, which is related, or which partitions quite strongly into feldspars. And we don't measure the feldspars very well with the spectral data, if at all. So that was quite interesting, because it was clearly showing that the geochemistry was adding a component that the spectral data was probably not modeling well. And then the rest of them were metallic elements, which described the sulfides quite well. So sulfur was one, obviously, and then the others were some of the minor elements that go into sulfides. I think thallium and tellurium, and I can't remember what the other one was. So what we found was that the geochemical elements were actually very complementary to what the spectral data were giving us. And then on the spectral side of things, the extractions, or the spectral features that were really giving us the most information, were not related to single features, but where we had a ratio of 2 things. So where we had a ratio of the magnesium absorption to the aluminium absorption, for example, that proved to be really important. And it is important because that's telling you how much of each of those 2 groups you got. And as a general rule of thumb, aluminium phyllosilicates are softer than ferromagnesium minerals. So that makes all the sense in the world. And the other was to do with water in the minerals, and specifically the transition from bound water in phyllosilicates and clays to unbound water in quartz and feldspar. So again, quite obvious, I guess, when you think about it, that would be a useful thing. So overall, you know, we at least we had good geological explanations for everything that we were doing. I hope that gives you a decent answer, David.
It's covered it. There's a really good case study. Thank you for sharing that. We have got a couple more questions. I do realise we're getting a bit short for time, but if you can see the one here from Katerina Savinova, just asking if you could just expand a little bit more on the mineral cutoffs and the thresholds and how they are determined with reference potentially to the Talc example that you showed.
Yeah, so when we do that, what we end up with, obviously, because we've got, you know, 1 millimeter to 1.5 millimeter square pixels, we get a lot of mixtures of minerals. It's quite rare, actually, depending on the grain size of the rock, obviously, but it's quite rare to see single minerals. So we've always got some kind of influence of other phases. And at some point, we've got to be able to still find talc, even where it might not be the predominant mineral. It might be the second or third mineral in a pixel. So to do that, we use this Boolean approach, and we know that talc's got certain absorption features that are unique to it, but they might be quite difficult to find first off. So what we do is we will use some of the bigger features, which could overlap with other minerals, so with amphiboles, for example, but we'll use them, and we'll use that as our first discrimination. We'll kick out everything, and we'll end up with, say, talc, amphibole, and biotite. Then we can separate the biotite out using a wavelength, and then we can use those smaller features to separate talc from amphibole. And what we've got to be very careful about is where we put those cutoffs so that we don't include amphibole with talc, or we don't cut too much of the talc out. So it's kind of a tricky, and we've tried to do this in an unsupervised mathematical way, but it's a very difficult thing to do. So it does require a little bit of an art from the spectral geologist as to where to draw those cutoffs, and a lot of examination of spectral data from a project. So that's essentially how we do it.
On a slightly related point, I guess I was curious about your opinion on how important you think pixel size is. Is the holy grail in spectral core imaging to go to finer resolution, or can we find a sweet spot that kind of fits the purpose, particularly for geomat applications where you tend to composite to assay intervals for broader scale application?
Yeah. It's a good question, and I think it's a bit of both. So the most important thing, obviously, is to be able to, in a cost-effective manner, look at all the core, because we can go all the way down to 0.2 millimeters if we so choose with these cameras. But by doing so, we slow our data collection down from north of 1,000 meters a day to probably 100 to 120 meters. And that just starts to make things slow and expensive, which means we know a lot about less core. So I guess from a geometallurgical perspective, my preference would always be to collect everything so that you've got a completely representative data set, as opposed to having to try and guess representativity from small little patches. Having said that, we do know that the next wave of spectral cameras coming out, what limits us is the width of the detector array that we've got. So it's like a cell phone camera that's got a specific resolution. So most of the cameras we use have got 384 pixels across track, and that governs how big the pixels are going to be, because we've got to fit a core box into that. However, the next generations of these are going to have 620 to 640 and even 1,000 pixels across track. So when we go to 1,000 pixels, suddenly we're going to be down at the 0.3 to 0.4 millimeter range, but with the same speed. So that's where the technology is going to go. We're going to be able to get better and better, just like your cell phone camera and your digital camera have got better resolution over time. We'll be able to get to those better resolutions without sacrificing anything else. The only thing we will have to cope with, though, is obviously vastly increased data volumes. And that's going to be a challenge to manage.
And just, I guess, one last question, and it can just be a one-word answer. If you could just attach one more sensor to your setup, what would you add? If you could add a XRF or I don't know, is there something that you think would really add a lot of value?
Ooh, that's a heck of a question. XRF, no, because it's too slow. I guess if we could do some kind of a you know, almost like an airport scan, if we could, even in a 2D sense, without getting into tomography, if we could just see where the sulfides were and speciate the sulfides using an X-ray, a penetrative X-ray, I think that would be an X-ray imaging. That would be a fantastic technology to add on. And there are a couple of guys out there doing that, but nothing that really gels just yet.
Okay, that's a good answer. We did have a question that, from Rocio, but I think we might ask you to answer that offline if that's possible, because it's relating a little bit more to the technicalities of the unsupervised approach to classifying, and I do appreciate that we're a little bit out of time. But it just does lead me to thank you one more time, Paul. It was a really, really excellent talk, and I think it's really well received, so thank you. Next week, we have Martin Politik, who is the Director of Technical Research at Wenco International Mining Systems, and he will be talking about open autonomy, breaking the closed stack. So we look forward to seeing you then. But for now, if there are any further questions, we will try and direct those over to Paul and get your response. But thank you again. Thanks to everyone online for joining us, and we'll see you next week.